Okay, we were talking about homogeneity, um, and the statement that just because you have curvature doesn't mean that you have. I mean, the issue is, do you have x-dependent terms in your v of r function? In other words, does v of r depend on x, or is v of r independent of x?
Right.
Okay, so does now the question is for what v now this is like solving for what possible forms, what forms can v sub r have if it is independent of x?
Mm-hmm.
What do we know about that? So, for
So
example,
other than the trivial case of just prefactor zero curvature.
No, I understand, but e.g. a sphere has v of r independent of x, right?
Mm-hmm.
So what does that mean? Is that like vacuum solutions to Einstein's equations, so to speak? Are they, what's the difference between having something which is for which, okay, what can we say about the homogeneous case where it's independent of x?
Right.
Can we, for example, derive an equation, a bulk equation for it in that case? Because then the x-dependent terms, that's where you really go to town and you can start computing, I claim. Because the x-dependence, there'll be many constraints on the x-dependence.
Right. So I mean, I think any surface of constant sectional curvature will have homogeneous V.
I don't think curvature is enough. What about higher order curvatures?
No. I'm not claiming that's a complete characterization, but certainly I think as a first case that's
I'm going to disagree with you because I think that there could be something which has zero sectional curvature, but some higher order curvatures. That are x dependent. I mean, it might not be true, but that's something to investigate, I think.
Okay.
Okay. So.
But the sectional curvature completely determines the Riemann tensor. So what would a higher order curvature be in that case?
Higher derivatives of the metric. What does the
those will be contained in the Riemann tensor.
Okay, let me try to understand this claim.
I think maybe I'm wrong, but
well, okay. Given a metric g mu nu, we can compute. I mean, the metric contains. Does the metric contain the same information as the Riemann tensor, or different amounts of information?
The metric and its first and second order derivatives will contain.
Okay, what about its third order derivative?
Yeah, I see what you mean.
I think it's out of the game because I think what you're doing is the Riemann tensor,
which will vanish for a metric connection, but for a weird connection won't.
Okay, I need to understand that claim. But essentially what you're doing in the Riemann tensor is you're fitting some kind of generalized ellipsoid to the space.
Right.
Right? Okay, but okay, now what are you making the statement that for a metric connection, what do you mean?
So when you're talking about higher order derivatives of the metric, I think ultimately they boil down to torsion parts.
I don't necessarily believe that. That's an asymmetry in the metric, right? G mu nu is not equal to G nu mu.
Right, but there's a theorem that says if you have a torsion-free metric, then it's characterized by the Levi-Civita connection.
Okay, so claim, Jonathan claim.
Okay, let me double check this, but
a torsion-free metric. Oops, torsion-free metric is equivalent, is characterized by what? By Christoffel symbols or what?
Yes.
By the way, let's talk about torsion freedom in our model. Mm-hmm. Is the metric always torsion free?
Well, in the way that I've defined it, it is axiomatically, because we assume that every, hyperedges have symmetrical distance.
Hold on. So metric is torsion free if there is symmetry in the geodesics, but I think that depends on, the model that that spatial slices are like undirected graphs is just a model. The true story is that, when you actualize connecting this to that, you do it through a light cone.
Mm-hmm. Right.
So it is not self-evident that, there are two light cones, right. There could be light cones from A to B and B to A, which are not symmetric.
Right.
So I don't think it's self-evident that it's torsion-free.
No, definitely. Obviously, as soon as you have hypersurfaces that are directed, then it's not going to be in general.
No, I understand that, but this is saying that the true measurement, the true way of deriving a spatial surface is by looking at, is by assuming some staticness. It's yet another limit that we have to take, right? Mm-hmm. To derive a spatial surface, we have to assume it's static.
Right.
Okay, and from that, so it is the case that, so we should be able to deduce for one of these things what its effective spatial connectivity is. Right? Because what we're doing there is we're saying if the successor, how the heck do we do this? Given 2 points, they are connected. They're given 2 points, they're connected. It's this exact construction. A is connected to B. No. If the successor of A, I think it's the successor of A and the successor of B. I don't know, some overlap condition between those. In other words, we should be able to derive from the evolution, we should be able to derive what an effective spatial slice is like.
Mm-hmm.
Okay. All right. So we're not necessarily torsion free, but
okay, so I think what we're looking for here is really some notion of conformal flatness, right? We want to. So in the GR case, you're saying you're in a space that's conformally flat if you can map it onto flat space by a conformal transformation.
Yep.
And I think that's the analog of the notion that one has homogeneity in some sense.
Okay, so
right.
let's see a claim. Okay, so condition. Well, okay, so that your claim is condition for homogeneity.
Mm-hmm.
This is a JG claim, is that well, wait a minute. Is that okay? Conformally flat.
Right. And if that claim is true, then my claim about the higher order derivatives is true. Because
right.
And therefore the claim about constant sectional curvature is correct, because there exist tensors for a pseudo-Riemannian manifold that are higher order tensor contractions of the metric, or higher order tensor derivatives of the metric, like the Cotton tensor, which is the third order one. But there are theorems which say the Cotton tensor in 3 dimensions, for instance, vanishes if and only if the manifold is conformally flat. And the same is true with the Weil tensor for n greater than or equal to 4, and so on.
Okay, third derivative of metric, and okay, so.
And so, yeah, one of the implications is that any manifold that has constant sectional curvature should be conformally flat.
Okay.
Which is that's obviously sufficient, but not necessary.
Any manifold with constant sectional curvature,
yeah,
is conformally flat. Sounds reasonable, but okay. But so the question is, if V of R is independent of X, then that implies, you claim, well, okay, if that's the case, then what can you say about the, okay, if V of R is independent of X, then V of R has a certain form. What can we say about that form? You're saying that the form, if it's independent of X, then okay, if it's independent of X, then V sub R of X is some function, okay, so if it's independent of X, it's just a function of R. What form can that function have? So I think it can still have a lot of freedom.
Yes. Well, certainly the the first 2 terms in the expansion can be free, because you could you can have conformally flat manifolds with
yeah, right. Claim JG claim first two terms. What the heck is the expansion in? It's in powers of R. First 2 terms in expansion. Well, that's a mess. An expansion in powers, and I put that in quotes, of R are undetermined.
Yes. I don't know if they're completely undetermined, but they're certainly not, completely constrained. Because you can have conformally flat manifolds with, I think, 0 and positive and probably negative Ricci curvature, definitely negative Ricci curvature.
Okay, but I don't believe in this expansion in powers thing, because I think the condition I mean, the condition has to be something, because there's no guarantee that this thing has power law at all. In fact, for many of these things, it's much wilder than that.
But as long as it's analytic, it'll have an expansion.
Who says it's analytic? It's not analytic if you change the value of d in r to the d. D equals 1.58 is not analytically expandable.
Mm-hmm. Right.
My guess is there's a more complicated condition.
Okay.
For example, it is not the case. Okay, so let's talk about a scale transformation, right? Oops. Scale transformation, change the value of r. What happens to this, v sub r? Right, because that's it. That would be so one possibility is that it could have simple scaling under that. So that's the case of a homogeneous thing, and that's where the normalization group potentially comes in. Does it approach? Okay, so the long time behavior is related to the large R behavior, I think.
Yes.
So, I mean, there's some complicated homogeneity condition that says as you increase the number of steps, you can be sensitive. Yeah.
Well, I mean, the large R condition is the long timescale condition.
No, because for a given time step.
Oh, sorry. R is the is the position is the origin position.
No, R is the size of the ball.
But these aren't balls.
What's that?
These aren't balls. These are geodesic cones.
Oh, okay. I was considering the spatial case.
But so the length of the geodesic cone is the time scale for a particular foliation.
I understand. It's the timescale for that slicing of the thing. It's the slice thickness, but I'm talking about the time since the origin.
Right. Okay.
Okay. Is the object that comes out scale invariant? Right? Is the structure after many steps scale invariant? i.e., is it a pure, oh yeah, this is very nice. Is it a pure power dependence in VR, V sub R?
Yes.
And that's pure in two senses. One is in the sense of spatial dependence. Is it spatially, homogeneous?
Right.
And is it scale free, i.e. R to the D?
Mm-hmm.
Okay. So we got our prefactor. Now, what you are looking at is the things beyond the prefactor that are X dependent, right?
Right.
Okay, so now what you hope to derive is the bulk equations for the spatial dependence of the things that are not in the prefactor.
Yes.
Now, in some sense, the prefactor is like, oh, the universe is uniformly expanding everywhere, the coordinates are changing, who cares?
Mm-hmm. Right.
Okay. That's not completely correct because the dimension is not this. The scaling factor determines the dimension. I mean, the exponent in the scaling determines the dimension.
Yeah.
Okay. Anyway, but let's come back to your. Okay, so your claim is that given. Okay, so now we're now computing the number of nodes function v sub r as a function of the space-time point x. Well, it's actually v sub t as a function of the space-time point x.
Right.
And as you vary the space-time point x, we know there is a relationship between neighboring points because there's lots of overlap in their resulting, in the cones that come out from them.
Right.
So now what we're describing is, in a sense, if we look at the derivative, right, of, okay, so this is going to be a covariant derivative claim.
Mm-hmm.
All right, so we have a quantity that somehow is varying from cone to cone as we go across the space.
Right.
Right? But there is some sense in which, let's see, there's a limit to how much variation there can be because there is a connection between cones as a result of the fact that they have lots of overlap.
Right.
Okay, so to what extent, if we define a, how is that related to the covariant derivative?
Well, I think it's exactly analogous to how you get the continuity equation using, covariant derivatives and things in fluid mechanics.
Okay, so let's remind myself how the covariant derivative works here. Okay, so distribution function evolves like this. Okay, so that's saying that at t plus 1, I see, the particles moving to the left or something simply wind up there, right? So that means that that there's a relationship between the x variation and the t variation.
Yes.
Okay.
Effectively because of particles having overlapping neighborhoods and only moving at finite speed.
Yes, that's right.
Which is, I think, identical to stating that, that cones have overlap, have effect, or that space-time events have overlapping cones, and the cones only propagate with a finite angle.
Yep.
And so, in the same way, I think in the fluid mechanics case, that allows you to derive the continuity equation on mass density. And I think here it allows you to derive an associated continuity equation on the actual space-time events.
And that continuity equation you claim is what?
It's at least it would be one component in the Einstein tensor. In the equation.
Why is it only one component?
Good question.
Okay, so let's understand this covariant derivative claim. So the claim is that if we write out the v as a function of, right, so this E sub A is the cone is going to go in multiple directions. So this is saying now that, because this, remember, has a momentum as well.
Yes, right. So maybe it's the whole Einstein tensor.
I think, well, what's the analogy of the momentum? So, in other words, you are...
You mean in the relativistic case?
Yes.
So depending on, the direct analog would just be momentum, but at a deeper level, it would be your shift vector, between hypersurfaces.
Okay, so hold on a second. There's a time shift vector.
Or time. It's actually not a vector. That's just a scalar.
No, it's a well, okay. Time shift between spatial hypersurfaces.
Yes. And then there's a spatial shift vector.
Okay. Spatial shift between hypersurfaces, basically.
Yes. And so obviously those are defined at every point on a given hypersurface.
Yep.
And so if my formalism is correct, then what's happening is that the time shift will ultimately correspond to an energy conservation statement. And the spatial shift will ultimately correspond to a momentum conservation statement.
Okay. Let me try to understand that. So the time shift I'm still not quite understanding. I mean, you're going to claim there's a continuity equation for the variation. That is, there's a V of R that's just doing its thing,
yes,
independent of position.
Right.
And that doing its thing independent of position essentially is defining things like the dimensionality of space and the overall curvature of space.
Right, but not the fine grain detail.
Right. So in particular, that's defining the overall cosmology, so to speak. Mm-hmm. Defining things like, do we live in a, three-dimensional, positively curved, universe?
Yes.
Okay. Then there's the question of the spatially dependent pieces on top of that. And there, the fundamental claim is that, let's think, that those spatial pieces, that the dependence on position, which I don't think you're writing here, but you're imagining that this RJK is dependent on position.
Yes. Well, I'm defining this CFT function for a particular event.
Right. Okay. But the main thing that you are then deriving is the statement that if this is dependent on position, those dependencies on position must have a relationship that corresponds to Einstein's equations.
Yes.
And by the way, that dependence in that case, in the vacuum case, is rather trivial. It's just the RJK equals 0. Right?
No.
I think so. I mean, that's the R mu nu equals 0. So, but these are dotted into time-like vectors.
Yes, but also you can have vacuum solutions with non-vanishing Riemann curvature. Ricci curvature, I mean, sorry.
No, you can't. R mu nu minus a half R G mu nu equals 0. And we could take that to be R mu nu equals T mu nu minus a half T G mu nu, so to speak. So if that's all 0, R mu nu is equal to 0.
But the trace part doesn't have to vanish.
For the vacuum?
I don't think so.
It depends on your vacuum.
Well, yes.
I mean, I thought that the classic version of the vacuum Einstein's equations is R mu nu equals 0.
Right. Yeah.
So if you've got a vacuum that is full of gunk, then R mu nu might be equal to a constant. Mm-hmm. Is that your claim?
Right.
That R mu nu is a constant rather than being 0. Okay, but so the first claim here is that in the case where that the simplest possibility is that R mu nu is equal to 0. Mm-hmm. And that is certainly a solution to that's certainly a possible scenario if VR of X is, that is basically the statement that VR of X is independent of X, I think.
Right.
Okay, if it is dependent on X, then it is your claim that that dependence can be, that there's a way of thinking about that dependence as being a T mu nu.
Right.
Okay. So claim is independence of X. Independence of X is R mu nu equals 0. Do we believe that? I don't think that's obviously correct. Wait a minute, because R doesn't have to be equal to 0. To be independent of X, you can still have a Ricci scalar, right? That would be right. in the case of a sphere.
Mm-hmm.
But no, I think it's more complicated, right? So it's that the, am I confused? There's nothing wrong with having a stable V of R, V sub R, that has a form that contains curvature. Is that a true statement?
Yeah, right. You can have conformally flat manifolds with any Ricci curvature, or with unconstrained Ricci curvature.
What is the condition for conformal flatness?
I only know how to define it in terms of the Riemann tensor, not in terms of the Ricci tensor.
Okay.
So I'm not sure. Yeah, I need to look more into what if any constraints are put on the Ricci curvature by conformal flatness.
Okay, let's find out the answer to that. I mean, okay, but then the dependence, okay, once it depends on X, okay, I'm still trying to wrap my head around this. Your claim is that dependence on X can be thought of as essentially the presence of T mu nu. Is that a true statement or not? Can it be dependent
yes,
on X without
right.
T mu nu?
I don't think so.
Okay, well, so if V doesn't depend on X, I see, then if V doesn't depend on X, then there can be an R term, but you claim there cannot be anything other than the trace of R mu nu.
Right. Yeah, I'm still uncomfortable with your statement, independence of X is R mu nu equals 0. It's independence of X implies R mu nu equals 0, but they're not equivalent statements.
Well, okay, so, but I want to understand, okay, implies R mu nu equals 0, right.
I mean,
okay.
R mu nu is 0 for the Schwarzschild metric, but that's sure as hell not independent of X.
Right. But wait a minute, but so...
And actually, even that's not quite correct, because you have independence, if you have a non-zero cosmological constant, you have independence of X.
Yes, you do.
So it's R mu, I think what you have is R mu nu equals, yeah, something else.
Well,
lambda G mu nu with some dimension normalization.
Well, let's understand that. Okay, so I think, look, I think you need to understand how your derivation works when it's independent of X. I mean, or do you think you understand that?
I think I understand. Well, I mean, I think I understand it to the extent that if it's independent of X, then I think, maybe I don't understand it.
Okay, let's come around again. I think this is good, actually. I think we're going to learn something from this, because I think the dependence on X is going to wind up being well, we need to understand this.
Yeah.
And then once we understand the dependence on X, I think deriving the higher order terms is not going to be that hard, because I think that corresponds to let me think about this for a second. Okay, so first of all, I still want to understand the covariant derivative idea.
Okay.
So the claim is that V of R's that are nearby at nearby X points are related. Okay?
Yes.
So if we look at a quantity that is being placed in the space-time, so to speak, then the variation of that quantity with spatial positions. Walk me through the meaning of a covariant derivative.
Yeah, so here's my way of thinking about it. So in the causal graph case, okay, so as I say, as you say, you've got these, you have these two space-time cones, and they're nearby, and we're interested in this quantity that is the volume of the cone as a function of its, of the number of hypersurfaces that it intersects.
Okay.
And so one way you can think of it is that cone 1 has been parallel transported onto cone 2.
Okay.
And so the question is then, so the Riemann curvature is, some fundamental measure of how much geometrical data is distorted by parallel transport. And that will include the value of this function. But the way that you think about that in terms of covariant derivatives is that it's the commutator, the Riemann curvature is the commutator of the covariant derivative.
Yes.
Right. The commutator of the covariant derivative tells you the degree to which geometrical data is failed to be preserved. So the discrete version of the Riemann curvature that I'm taking from Jan Olivier's paper is exactly this measure. It's giving you, in effect, a discrete analog of the commutator of the covariant derivative operator for these nearby,
and what's the analogy of that? If you don't do all this, I see. So it's taking a geodesic ball, basically, transporting the geodesic ball, and finding out what happens to it.
Right. Right.
Okay, but then again, okay, so the true covariant derivative of the universe, so to speak, as far as we know it today, contains both external general covariance type stuff and internal gauge invariance type stuff.
Yes.
Let me understand. Okay, I still don't completely understand. I mean, I understand how you get, how you can get a commutator, how doing those two steps of parallel transport, going different ways around the rectangle, gives you a measure of what's going on.
Right.
But trying to understand, in terms of the individual transport from here to there, the issue is the cone is distorted by that transport. And so, so if you're looking at a quantity that's defined in one place, right, it's distorted just by virtue of moving the measuring point to somewhere else. That's the covariant derivative. Yeah, okay, fine. Okay.
Exactly.
So
so the way that that's done with Olivier's formalism is you say the transportation is in terms of these, volume measure transportations that you can quantify using Wasserstein distances and things. And then you can say, if we have a point in this if we have a point in this geodesic bundle and it's parallel transported to a nearby point in this other geodesic bundle, and then, and you consider the reverse operation, how much of a particular quantity is changed.
Okay.
And that's supposedly the direct discrete analog of a covariant derivative commutator for a hypergraph.
Okay. Okay. All right. So then the question is, to what extent are the higher order corrections generic? To what extent, like in the cellular automaton fluid case, the presence of these terms, well, the value of the viscosity depended on the detailed model.
Right. Right.
So in this case, what do we expect will happen there? So in other words, we've got something where
So I suppose what that's really saying is that the Einstein equations will be fairly generic between different rule sets.
Yeah.
But the higher order corrections will probably depend sensitively on exactly what.
And things like the value of kappa or whatever it's called.
Right. Right.
And the value of the dimension.
Yes.
These are all actual things that have to come out.
Yes. Right.
My guess is those two come out together. The overall curvature and the dimension are closely related. And see, the surprising thing is that the overall dimension is measurable. You might have thought that V of R independent of X would not have measurable consequences, but it does.
Right.
And the overall curvature it implies is also a measurable quantity.
Right.
So the question would be, is there a higher order measurable quantity there?
That would be exciting.
Right. So let's think about that for a second, okay? So what we've got is this thing that, okay, we measure in the dimension of space, we're measuring the curvature of space, and in principle, we could perfectly well have a higher order correction to that. Right? There's nothing to say that V of R should have only quadratic dependence. It has the form R to the D times 1 plus constant times R squared times whatever, right? Could be anything we want. And how would that show up? That would show up, interesting. Okay, that will show up in the large scale structure of space-time, right? Because that would show up in something, I mean, interestingly, dimension is very locally measurable.
Yes. You can just diffuse a gas or something.
Yeah. Or curvature, on the other hand, well, that's really the statement that in our current universe, it's really close to R cubed times 1 plus, something R squared.
Yes.
Right?
And even the R squared bit is quite small.
Right. That's a really good approximation.
Right.
But that doesn't mean it's the whole story.
Right. And I suspect it's kind of similar. There are results about how if you look at, for a fluid parcel or something, even in the Navier-Stokes case, an individual fluid parcel can be viewed as effectively obeying Euler's equations. And it's only when you have, large numbers of them that
sure.
viscosity and things.
Okay, let's talk about cosmology for a second, okay? So, in the current solutions to Einstein's equations in fixed dimension D,
yep.
In vacuum Einstein's equations, not correct for actual matter, but forget that.
Yep.
we can have a curvature, well, we have a cosmological constant that's undetermined. Without matter, otherwise, what do we have? We have various solutions for r mu nu equals 0 has various solutions for the metric, correct?
Right.
Which have measurably different Riemann tensors.
Yes.
Corresponding to various, so what are some of those solutions?
Schwarzschild would be one example.
Fair enough. Okay, so those solutions have the feature that they are not uniform solutions in the sense that they have a, well, in the case of Schwarzschild, there's uniform except at a point, right?
Right. But Kerr is also a vacuum solution.
Right, it's also uniform except at a point, right?
Yeah. Which I think will be generally true.
No,
wait, hang on. There's like the Kasner metric is a vacuum solution. That's not uniform.
What is that? It has some kind of power law thingy in it?
Yeah, right.
What does it have?
It has a dependence on spatial coordinates squared.
Let's look that solution up. That may be relevant to us. Okay, so wait a minute. So let's look at, okay, so we're looking first of all at vacuum solutions.
Right. I'm pretty sure the Kasner metric can't be, it's because it's non-isotropic, so it has to be non-uniform.
Okay, so the claim here is, right, I mean, Einstein's equation, so in our situation, we're saying that it appears that we're really close to r cubed times 1 plus lambda r squared.
Yes.
A curious claim at the best of times. Okay, were it to be r to the 3 plus delta or something, we then need to understand, you know, I remember from years ago, people testing the dimension of space-time by looking at Coulomb's law and things like this.
Yeah.
Right. And I can't find, if you can find a reference for that, it would be really helpful. I mean,
sure.
I remember that
I'm sure that, I remember seeing some papers by like Teller and Dyson and other random folks, if not commenting, at least commenting on the results, if not stating them.
Okay, if you can find a reference, it'd be really helpful, because it'd be nice to know what the actual bounds are.
Yes.
Because they may be really cruddy for some distance scales.
If anything in cosmology if we can go by any of the other results in cosmology, I think it probably will be quite cruddy.
Principle of equivalence is verified to 1 part in 10 to the 15. That's not so cruddy.
That's fair.
Okay, so let me think about this for a second. So then essentially the measurable effect will be that, yeah, I mean, on a large scale, it's simply, you know, what we believe right now is, okay, on a large scale, the universe seems to have some curvature, although it's pretty close to, isn't it the case that it's pretty close to the k equals 0 situation?
Yeah, right. Very, very close. That's the flatness problem.
No, I understand that, but I mean, isn't it, but, so the universe, in our way of talking about it, is really close to being pure r cubed.
Right. Ooh, interesting. Okay.
What?
We've got, we have a value of 4 minus 5.3 plus or minus 2.5 times 10 to the minus 7.
Okay, send me the
for the dimension of space-time.
Send me the link. I remembered that there were results like that. I just didn't remember whether.
Yeah, this is not a cosmological one though. This is a.
No, I understand. It's a local
QED
lab.
one.
Yeah, that's what I thought. That's what I thought they were. I don't believe there are cosmological ones.
Right.
How would you figure it out? Let me look at this. Oh, bluff.
Oh, actually, I can email you the PDF.
Yeah. I can log in using one of my several academic accounts, but
it would. Yeah, it's probably quicker of me to email the PDF.
How would you measure the dimension of space from cosmology?
Interesting.
I can ask some cosmology friend.
Yeah.
Oh, I know those characters. Wow, he was involved in this. All right. Yeah, bubble. That's a very questionable. Oh, come on. That's using dimensional regularization and just imagining that the D in dimensional regularization is real.
Right.
It's an amusing idea, actually. It's an amusing idea, since one has actually computed a bunch of these things using, yeah, I mean, all you have to do is look at the calculation of G-2 in dimensional regularization.
Right.
Boy, I even did those calculations at one point. In fact, I even have some paper somewhere about, okay, all right, fine. Yeah, I mean, so the question is, what happens to the renormalizability of QED? Obviously, as it gets to be different from 4, QED is no longer renormalizable.
Right.
So what? A small deviation. Okay, so that would be, look, in our model, this question of a deviation, that's a good point though. Okay, I give these guys credit for the fact that I hadn't thought of that point, that you can simply use the dimensional regularization computation to work out, yeah, in other words, at what point is the deviation of G-2, let's see whether we can, boy, this is, I mean, we can use this calculation. Okay, let's see.
I'm wondering about the cosmology case.
Mm-hmm.
And I don't know, this may be too dependent on, solutions to the cosmological constant problem and stuff. But can't you do something with the fact that the, 0-point energy of the universe, like the observable cosmological vacuum energy density is proportional to the Planck length to the -4, and use that to get, you're basically getting cosmological constraints on the negative exponent by measuring vacuum energy density.
No, because I mean that depends on, I mean that's the dimensional regularization analog. That's the analog of dimensional regularization for the normal ordering of the 0-point modes, which I just don't. I mean, so what? I mean, so the thing is huge, and whether it's huge and cancelled one way or cancelled another way doesn't seem to me to make any difference.
Yeah. Right. Okay. Yeah. That's what I said. I think it may just be too dependent on.
Yeah, I think it depends on that particular solution, because, but let's think about that.
The only other thing I can think of is, when you do.
Okay, can we just write down the Friedman-Robertson-Walker equations? Don't they have a dimension term in them? Aren't they just simple? I mean, by the time you've integrated over a hypersphere somewhere, don't they just have simple dependence?
On dimension?
Yeah, because and nominally, I mean, not
Well,
structurally.
in the scale factor,
How?
I mean, the scale factor will scale like like the radius of the universe to the power of the dimension. The A term in the Friedmann equation.
Okay, well, so that's our answer. Can we write that down? What is that equation?
It's in my paper.
Okay.
Page 45 for the Friedmann equation.
Okay. Okay. So h of t is the Hubble expansion rate.
Right.
And, all right, where's the dimension in all of this?
So the scale factor A implicitly defines a dimensionality, I think.
Why? Do you think the 8 pi is dimension dependent?
I believe so.
Let's work it out. It's the volume of some, I mean, that, 4 pi squared r squared is the volume of, well, so where does the 8 pi come from? And then the next question is, does anybody care what that 8 pi is? Let's imagine that pi was dimension dependent, so to speak. Does it matter? Probably matters. Oh, yeah. Yes, it matters to the value of rho.
Right.
Which sort of matters to the total mass density of the universe.
Right. Right. Densities need volumes.
Indeed. But I mean, the fact is that since the mass, the question is what happens to the various kinds of dark matter, although that's a somewhat more local question, if you change the 8 pi.
Mm-hmm.
All right, so where does the 8 pi come from? So yeah, I mean, this is a good question. Is the dependence, is dimension, one question is dimensional regularization actually the correct way of analytically continuing? It's probably fine. It's probably just fine, at least for small variations of D. Let's hope we don't.
Right. Okay, yeah. So yeah, the 8 pi is, I think, dimension dependent because it emerges because when you do the sort of modeling state of matter of the universe as a perfect fluid, you do a rescaling of the mass density and the pressure.
Oh, yeah, the 1/3. Yeah. The 1/3 in the formula for the p minus 1/3 rho.
Yes.
That 1/3, I'm sure, is the dimension of space.
Right. Yes. But actually, the 8 pi g bit is also, because that's a term that comes from lambda c squared over 8 pi g.
Okay.
In the rescaling.
Okay. So it's dimension dependent.
Yep.
Well, there's our partial answer. I mean, that tells us. Okay. But in general, if we were to imagine, all right, so we've got these equations that I'm trying to understand. Is there a general version of the homogeneous Einstein equations for arbitrary V sub r?
Right.
In other words, where it doesn't specifically depend on
a power law relation.
Yeah.
Yeah.
In other words, a way of setting that up that's purely dependent on a kind of metric.
Yeah, but this gets back to the problem that we ran into the other day, where, as far as I could tell, that no one has succeeded in coming up with anything like an exact, closed form value for metric volume elements and things. That they all seem to depend for even for very simple Riemannian manifolds. They all seem to be doing some kind of power series expansion. I mean, it's possible we could expand in some other kind of function, but
yeah,
we could do. I'm not sure if anyone's tried like a Fourier series or something.
right. I'm about to run out of time here, but
Okay.
let's go back to the Schwarzschild solution. And
yes, what would you like me to do with that? What's the current status of it?
Well, the current status is nothing happened after. The only thing that happened after you departed, I think, was that we figured out this transitive reduction way of going from, of basically deriving, given a bunch of space-time points, given a bunch of points arranged in some way in space that define a bunch of light cones, we can get a causal network from that. So in other words, if you throw down points arranged in space-time, arranged according to your favorite metric, I assume.
Right.
I don't really know though. No. Explain something to me. The square root of G determines the density of points as a function of X and T.
Yes.
Is that correct?
Yes.
Okay, so in the Schwarzschild metric, the square root of T in somebody's favorite coordinate system, right?
Mm.
We need to get what that square root of T is as a function of X and T in somebody's favorite coordinate system. And then from that, using this, we can, I mean, it's a little bit of a hacky way to do it. We can throw down random points distributed according to that distribution of square root of G density.
Yes.
And then from that, we can derive a randomized causal network.
Right. But I don't even see why we need to do the randomization thing.
Okay, well, you just do grids in X and T.
Exactly. We know the metric volume element. We can just, we in effect, we have a function that tells us for a given vertex, how many neighbors does it have?
Okay, so well, okay.
So I think we can do it entirely deterministically.
All right, okay, fine. But can you do a spatial slice? Because then we could look at the JD6 in a spatial slice.
Yeah, well, it should be possible to construct a causal network this way. I mean...
No, but I'm talking about a space network.
Yeah, I know. Well, if you have a causal graph, then the...
Yeah, right.
Constructing a space network is just taking a slice through it. You just have to take some,
thickened slice.
Space-like separated, or not non-time-like separated collection of edges.
Yeah. All right. Well, why don't you try and do that? Because it'd be really nice to show an example of JD6 in the Schwarzschild metric.
Yeah.
I am very optimistic that we're going to be able to find some way of looking at basically constraining, well, at least the long-time behavior of these models. I mean, we've got one big constraint, which is the 3.
Yes.
And I claim the 3, the asymptotic flatness, and that's, but this is really revealing the fact that there could be something more than that, and that it doesn't prevent there from being locally, the claim is it doesn't prevent there locally. See, this is an interesting claim, that if V sub R has some wild form, there can still be local general relativity, I claim.
Right.
While still implying something different about the large scale, quotes, dimensional structure of space-time.
Right. So it's basically like saying that, the higher order corrections don't even have to be polynomials.
Right. Right, but what I'm saying is that your derivation, hopefully, of the local version of general relativity, right, will not depend on the fact that V sub R has wild extra nonsense in it.
No.
Right? It's purely statements about the bundles of JD6 and so on, and conservation laws for bundles of JD6.
Right.
But nevertheless, that V sub R has observational consequences in the universe, just like the exceptionally obvious one that's been known for 1,000 years. I don't think it was really recognized before that there are 3 dimensions in space.
Right.
Interesting. Well, I would predict that I bet there's no local deviation, but I bet that there's there might be. Okay, the deviations will come at very small scales and probably at very large scales, because most likely if you have some function v sub r, what that's saying is for some large range of values of r, the thing is behaving just like r cubed.
Yes.
But if there's a correction like an r squared correction, that will happen at very large r, and there could be perfectly well some non-analytic weird correction at very small r.
Right.
Very interesting. Okay. Well, all right. I need to disappear. But okay. By the way, how is the Wolfram model multi-way system thing?
So I got a little bit worried because I was producing the causal graphs that my thing was producing disagree in some corner cases from the ones that Max's code produces. So I'm currently trying to track down that bug.
Have you talked to Max about it?
No, not yet, but I will do.
Okay. Why don't you try and resolve that? I mean, look, in the path that I'm on right now, I'm going to be hopefully hitting that stuff tonight, tomorrow, on that time scale.
Okay.
I mean, I don't know. I'm hoping that what I wrote previously about the updating orders stuff is okay. In which case, I've largely written most of the string updating stuff, and then I'm on to the Wolfram model updating stuff.
Right. But what I wanted to check was, so given that you have causal graph stuff in Wolfram model, you definitely still want causal graphs to be in the multi-way system Wolfram model.
Absolutely, because I want to show how a Wolfram model which is not causal invariant generates a more complicated causal graph.
Okay.
Right, and then how the peel-off works. And for example, here's a little exercise for you. Okay, we know that a bunch of rules sometimes lead to connected results and sometimes disconnected results.
Yes.
What consequence does that have in the multi-way system?
Yeah, interesting.
Because what that means is, I mean, I just need to look at some of them, but I mean, once it's disconnected, it ain't connecting again.
Right.
So that means that causally, I think what that means is a piece of the causal graph breaks off.
Right.
And
if nothing else, you have an irreconcilable bifurcation of the multi-way system.
Yes, but I think that can't happen. I mean, obviously, you can't have a diamond lemma if the thing is broken off.
Yes, right.
So I think that cannot happen in causal invariant cases.
Yes, this is true.
I think. I mean, which is to say that.
No, wait. No. I don't think that's necessarily the case. Because you can still have a thing. You can still have something which bifurcates, but it's, the two arms of the bifurcation still converge on something. It's just that the thing they converge on is also disconnected. But maybe that's not true. Yeah, I need to investigate. It's not immediately obvious to me whether they can be causally invariant or not.
Yeah, I mean, that seems to have, by the way, okay, once we get through, I mean, so we're not going to finish the problem of the general relativity problem. It'd be cool to compute. I mean, I think we just need to get to the starting gate there.
Yeah.
Then the quantum mechanics case. I really would like to understand the team you knew, that the presence of matter and your interpretation of that, because I think that's in
the GR case.
Yes, because and then the thing for the quantum case, I believe, is that we need to look at essentially Green's functions and correlation functions. We need to look at the effect on one of these systems of a small perturbation and this whole business about states versus observables.
Yes. I mean, that much I think I understand.
Okay.
The Green's functions, impulse reaction stuff, not so much.
Okay.
But I think
yeah.
I know enough to be able to write something vaguely coherent about, operators and uncertainty and
Why don't
things.
you start writing it?
Yeah, I think I will soon.
Okay. Boy, it is completely crazy to finish this project in the next few weeks, but let's do it anyway. I mean,
yeah, I think it'll happen.
Yeah, I mean, it's I mean, the volume of stuff that we've all produced is good. It's good. This is good. This is what one hopes for, rather than having a microscopic amount of stuff produced over a long period of time.
Right.
The trick is a macroscopic amount of stuff produced in a small period of time. All right, I need to go.
Okay.
To be continued. See you
sure.
later.
I'll be around later, by the way, if you want to.
Okay, great. Yeah, I'm mostly going to be trying to write some stuff, but I will be happy to continue this.
Okay, right.
See you later.
Bye.
Bye.